Right. So let's start with the discussion of the interference concept that we discussed last time, and understand a few more advanced properties and aspects of interference. So we were discussing interference in detail last time. So interference was defined as the superposition of, we had seen in the basic derivation two waves, but it can be more than that also. So the superposition of two or more, basically multiple waves of identical frequencies traveling along the same direction on a string. That particular phenomena is called interference. And here, remember, when we are talking about waves, we are still specifically in the domain of transverse mechanical waves. Okay. We will come to sound waves and their interference, etc. in the next chapter. We are still in the domain of transverse mechanical waves. That particular number. Okay, so let's quickly recap the mathematics part. So what we saw is that two waves, if you start with a situation of two waves interfering, later we'll discuss multiple. So two waves of identical frequency traveling in the same direction. So let's say one of the waves is designated by this equation, A1 sine omega t minus kx, and the other one is A2 sine omega t minus kx plus some phase difference, say delta phi. So understand over here, this wave is coming from y1 is a wave created by a simple harmonic oscillator, which is basically the source, which acts like the source of the wave. So let's say it's source S1 of frequency F and amplitude E1. So the wave it creates, the wave Y1 also has a frequency equal to F only, and therefore omega equal to 2 pi F. And accordingly, it has a wavelength of V by F or 1 by F square root T by mu, because it's propagating along a certain string. So as it is propagating along that string has the property of whatever square root T by mu. So that means, okay. So it has a K which is accordingly 2 pi by lambda or omega by V, okay, because V is equal to omega by K, like that. So that's the property, okay. And similarly, the other equation y2 equal to a2 sine omega t minus kx plus some phase difference. So this is the wave created by a second source, S2, which is having same frequency, identical frequency. That is the necessary condition, F. And amplitude may or may not be the same. So we have taken general case amplitude 8. So that's why naturally if the frequency is the same, lambda will be the same, okay, 1 by F square root T by mu. And that's why K will also automatically be the same. It's omega by V or 2 pi by lambda. So as long as the two sources, so the important point here is that as long as the two sources are simple harmonic oscillators of identical frequency, they will create waves which have identical frequency and identical wavelength. And of course, the waves are traveling in the same direction along the string. That's also the necessary condition. Because we'll also see later today that if waves are traveling in the opposite direction, then they create a different phenomena. That is not called interference. So for interference, the necessary condition is that any number of waves can interfere. It need not be just two, so two or more. But the necessary condition is this, that they should have identical frequencies firstly, and they should be traveling along the same direction. ये दोनों चीजें are part of the definition of the process of interference. Okay, they are the necessary and sufficient condition, you can say, for interference to happen. So now interference is nothing but the superposition of these two. So it is y1 plus y2, and we had seen all that mathematics last time, that the net y becomes nothing but some net amplitude into sine, same angular frequency, same angular wave number, and some phase constant, which you might denote by any symbol you like. So I'm just going with the symbol epsilon. So this is what happens when we apply all that, trigonometric equation kind of concept to adding these two quantities, y1 and y2, which we have seen before. And in this, of course, the standard formula that you have is that the net amplitude becomes root of E1 square plus E2 square plus 2 E1 E2 cos of delta phi. And this resultant phase constant epsilon becomes tan inverse of E2 sine delta phi upon E1 plus E2 cos delta. And as we discussed, the easier way to interpret this is that just remember it as a phasor diagram. Think of E1 and E2 like not vector quantities, because they are not vectors, but they are quantities which have phase angle. So if the two waves are not in phase, they have some phase difference delta phi, then that will show up in our amplitude phasor diagram. This method is called, this diagram here is called the phasor diagram instead of a vector diagram, because it represents quantities which have phase, which is nothing but waves of amplitude E1 and E2. So in this phasor diagram, it is nothing but the third side to complete the triangle, just like a vector addition, which becomes the resultant amplitude or the net amplitude. And this particular angle here becomes nothing but that. So you know that this diagram corresponds to this formula, and it corresponds to this formula for the angle. So that's a very easy way to interpret and remember this. Okay. Now let's move on to some more important special aspects of this. Okay. So all this you've done in the last lecture, so don't worry about it. Okay. So first and foremost, you can see that delta phi is called the phase difference between the two waves. Phase difference between the interfering waves, you can say, or the superposing waves. So that delta phi, it actually determines the value of the net amplitude. You can see that since cos delta phi has a range of values between +1 and -1, because delta phi here could be anything. It could be from minus to plus infinity. But you know that cos is a circular function, so whatever the value of the angle to which we are applying the cos function, argument जो भी value है, उसका range of values of function का क्या होता है between -1 and +1. So therefore, from that we can see that our net amplitude cannot be larger than the sum of the amplitudes. That you can understand from that formula. Cos delta phi जब +1 होगा तब ऐसा हो जाएगा, and this cannot be less than the difference of the amplitudes. Okay. So the maximum value of net amplitude that we can get is this. Okay. So in fact, that maximum condition is given a special name, and that is called constructive interference. So in fact, what happens is, for the condition delta phi equal to 2n pi, we get cos delta phi equal to +1, and the net amplitude becomes equal to E1 plus E2, which is basically the maxima. So this maxima condition is given a special name. Okay, this particular condition, that delta phi becomes this, and therefore all this happens. This is called the special case of constructive interference. So whenever you hear the term interference, it is a general term for the superposition like this. Okay, but when you hear the term constructive interference, वो specifically किस type का superposition हो रहा है? That type of superposition where the amplitude, resultant amplitude is getting maximized, or the phase difference between the, or in very simple terms you can say that the waves are in phase. 2 and pi का मतलब 0 ही होता है ना, so they are in phase. Therefore, the amplitudes are actually adding up, and you are getting the maximum possible amplitude. So this particular case is called constructive interference. So in simple language, we can say constructive interference is the result of superposition of waves of identical frequency which are in phase, okay, resulting in maximum amplitude. Okay, so this is from interference of waves that are in phase. That is, their equivalent phase difference is 0. 2 and pi is equivalent to 0. Okay, and that is resulting in the net amplitude becoming the maxima, which is A1 plus A. So that is the proper definition of constructive interference. Okay, so like you can start with just a note of this. These formulae and all you have seen last time, so you need not note down again. You just go through a recap of this, and in that formula you can understand कि क्यों ये A1 plus A2 हो जाएगा, because the moment cos delta phi is becoming positive of 1, the quantity inside the square root is becoming A1 plus A2 whole square. So that is how we get the condition for constructive interference, which is this. Okay, so we can start with this. Just make a quick note of this point. So the condition for constructive interference is that the interfering wave should be in phase. So mathematically, इसका मतलब क्या है, that the phase difference should be of the type 2 and pi, where n could be any integer. So it could be 0, plus minus 1, plus minus 2, etc. Okay, that's another thing you should understand over here. N is basically any integer. It can be negative also, but it has to have an integer value. Aditya, fundamental frequency is a different thing. That is related to something called the resonant modes of vibration that occur in something called standing waves. Okay. So we will be coming to that little bit later, probably in the next lecture. We might start with standing waves today, depending on how many doubts people have. But just to tell you over here, fundamental frequency is not something related to interference, but it is related to another type of superposition, which is called standing waves or stationary waves. So it is not a term that comes in interference. In fact, after interference, standing waves will be the last thing that we'll be doing in transverse waves. Then we are done with transverse mechanical waves. Okay, so hope this part is clear over here. So the condition for constructive interference is delta phi should be a even multiple of pi. 2 and pi hona chahiye, including 0 of course. And what that condition results in is that the net amplitude becomes the sum of the amplitudes. It becomes A1 plus A2. Similarly, we have destructive interference. That is the situation when you get the minima. The opposite of this. So similarly, for delta phi being, you can write it as 2n plus 1 or minus 1, whatever you like. 2n minus 1 pi cos delta phi becomes negative of 1. And consequently, the net amplitude becomes magnitude of A1 minus A2. Never write it as A1 minus A2 because remember, amplitude cannot be a negative quantity, whereas A2 might be larger than A1. So it's basically the difference of the two amplitudes. So that condition, or that is the minimum. So this is the condition for destructive interference. So this phenomena is called destructive interference. This is called destructive interference. That is the other extreme case of interference. This is the condition for destructive interference. So what happens in destructive interference is that, of course, here n is plus minus 1 plus minus 2, in fact starting from 0, if n is 0 also. Okay, so the definition here becomes that the interfering waves, if are perfectly out of phase. ये meaning होता है. Okay. Then the net amplitude becomes the minimum possible value, which is mod of A1 minus A2. And that phenomena is called destructive interference. So how I'm saying perfectly out of phase is because delta phi being 2n minus 1 pi means that y1 being E1 sine omega t minus kx, y2 being E2 sine omega t minus kx plus an odd multiple of pi can be written then like this. Y2 can be written as minus of E2 sine omega t minus kx. It can be written like this. And the reason for that is that simple trigonometry, that sine of theta plus 2n minus 1 pi is minus sine. For example, sine of theta plus pi is minus sine theta. Sine of theta plus 3 pi is minus sine theta. Sine of theta minus 3 pi or minus pi or whatever, it's minus sine theta. So like that, any odd multiple of pi over here, this term results in this. So therefore, your y net, which is y1 plus y2, results in E1 minus E2 sine omega t minus kx. So you can see that it results in the net amplitude becoming the modulus of A1 minus A2. And that is a condition of destructive interference. So need not even interpret it from that complicated formula for net amplitude. You can just understand कि मेरा phase difference term अगर odd multiple of pi बन जाता है, then this whole term can be written as, instead of A2 sine omega t minus kx plus some phase difference, it can be just written as minus A2 sine omega. So that's why you can see that when they are adding up, this wave and this wave are exactly out of phase. That's the important thing. So that's what I meant by saying that they are perfectly out of phase. So y1 and y2 are perfectly out of phase, or in opposite phase, you can say. Out of phase both them kabhi, or we say it is in opposite phase. At a given position, if one wave is creating a crest, the other one must be perfectly creating a trough. Whereas when they are in phase, both are creating crests at the same positions. Both are creating troughs at the same positions. Okay? So these are all common terminology that we use for the phase condition for constructive and destructive. Okay? So they are just opposite of each other. Constructive में क्या होता है? They are in phase. So crests and crests are overlapping, troughs and troughs are overlapping. But destructive में exactly उल्टा हो रहा है. They are in exact opposite phase or perfectly out of phase. That means wherever the first source was tending to create a crest, at that same position it should be overlapped with the trough of the second wave and vice versa. Okay, so a lot of our solving cases and problems and all will be specifically based on these two special cases of interference, constructive interference and destructive interference. But interference in general is something much wider. That means the resultant amplitude can be anything in between A1 minus A2, or the difference of A1 and A2 and A1 plus A2. The two are just the extreme special cases. Whereas they can take any other value in between also, depending on what the phase difference is. Okay, so this is the important concept over here. Okay, so as I said, constructive and destructive are two special cases. Now let's come to another aspect to understand. Now, one more special case to discuss about interference. If the amplitudes of the two waves are same, for y1 and y2, then we can simplify this formula a little bit. This net amplitude formula, like you've done in vector algebra, this formula becomes e into square root of 2 into 1 plus cos delta phi, which you can further reduce to 2a cos delta phi by 2. But remember, this will come with a mod because you remove the square root. So the net amplitude will come as this kind of form. And similarly, epsilon, which was tan inverse e2 sine phi upon e1 plus e2 cos phi, becomes sine of that delta phi. And actually, this is also delta here, divided by 1 plus cos delta phi, which you can use trigonometry further to solve. So this becomes like this. Epsilon becomes delta phi by 2. So this is the special formula that you can reduce it to whenever your amplitudes of the interfering waves are the same. You need not use this lengthy formula. You can see. And from this you can also see that in this case, the net amplitude becomes 2a for constructive and 0 for destructive. So that's another interesting factor. There is complete cancellation when there is destructive interference of waves of identical amplitude. Okay, so hope these formulae are clear to all of you people. Now the next thing, so you'll get used to all these formulae while solving problems probably. Then the next thing is the discussion about power. So you know the general formula of power was half mu v omega square e square, or that's the same thing as half square root of tension into linear mass density into omega square into a square. So therefore, when we have the formula that since net amplitude is equal to square root of a1 square plus a2 square plus 2a1 a2 cos delta phi, we can say that net amplitude square is equal to a1 square plus a2 square plus 2a1 a2 cos delta phi, and power of the first incident wave is proportional to a1 square, power of the second one is proportional to a2 square, and the resultant power or the net power transmitted is proportional to net amplitude square, where the constant of proportionality will be the same for all of them. The constant of proportionality will be half square root t mu into omega square, because remember all the three waves, I mean the two interfering waves and the resultant wave, they all have the same frequency term and they are propagating through the same medium. So looking at this proportionality, we can convert this formula into a power formula, that the net power transmitted is equal to this relationship between the power of the individual waves. It is this kind of a formula. So this also becomes an important additional formula, that just like the resultant amplitude in terms of the individual amplitudes of the incident waves or the interfering waves, like that we can calculate the net power, okay, or the power of the resultant wave it transmitted in terms of P1 and P2 are the power transmitted by wave Y1 or the power transmitted by wave Y2. Okay. And again from this, just continuing on that, you will also see that the maximum power that you can get is P1 plus P2 plus 2 root P1 P2. Okay, and that happens for delta phi to be 2 and 5, or basically what we call the constructive interference case. So this can also be written as square root of P1 plus square root of P2 whole square. The maximum of power is square root of P1 plus square root of P2 whole square. And similarly, you will see that the minimum power for the destructive interference case will come out to be, just use the same application but put cos delta phi as minus 1 and we'll get this. So this occurs for delta phi equal to 2n minus 1 pi, or what we know as the destructive interference case. You should also know this as a rule of thumb, that destructive interference will result in a net power which will be of this kind of formula. Constructive interference will result in net power which will be this kind of relationship of P1 and P2. Just like in this case the amplitude becomes A1 plus A2, and the destructive interference case the amplitude becomes the difference of A1 and A2. So see, likewise you have a correlating formula for the power. So just while doing numerical questions and analyzing the relationship between the powers, okay, this becomes an important analysis. It's nothing new. There's no new information here. It's just that you are reorganizing the equation for net amplitude into net power, because power is proportional to square of amplitude. As simple as that. Okay, so let's do some questions now based on all this. Okay, so let's now move on to some questions based on interference. So for example, suppose we have something like this. Y1 is equal to, say, 2.0 millimeters sine of omega t minus px. Y2 is equal to 1.8 millimeters into sine omega t minus kx plus pi by 3. Okay. So you want to find, or let's make this a little simple to begin with this one. Okay, so let's take 2.0 and 2.0. Both are having same amplitude. So calculate the net amplitude as a result of superposition of y1 and y2. Okay. And secondly, if the superposition results in a net transmitted power of P net, then find the ratio of this P net is to P1, where P1 is power transmitted through wave 1. That why find the frequency of oscillation of any medium particle as a result of this superposition, and find the resultant waves wavelength. What is the resultant waves wavelength? For that, it is also given to us that omega is 200 pi radians per second and t is equal to pi by 40 radians per centimeter. We have to also find propagation speed. All these, okay. So this will cover the basics of interference without too much difficulty in solving the question. This is like your typical, more or less formula-based type of questions, the type you can expect in your mains level questions. Just try this out. Then we come to a couple of more tricky type of situations where the phase difference is not given to us directly, and we have to figure out the phase difference from some other information given in question. Okay, people, send me your answers, please, for this question. Yes, that's correct. Ashwin, Aditya, Siddharth, your answers are all correct. So you can do this question, as you can see, more or less formula based only. You have y1 equal to 2 sine omega t minus kx and y2 equal to 2 sine omega t minus kx plus pi by 3, where omega is 200 pi radians per second, y is in millimeters, and k is pi by 40 radians per centimeter. You can see all these things. So coming back to this, you can see that A1 is equal to A2 equal to A, okay, and phase difference is equal to pi by 3 or 60 degrees. Okay. You can go with either the formula based method or you can go with the diagram or whatever. So A net, I'll use this formula now, is 2A cos delta phi by 2. So 2 into 2 into 2 root 3 millimeters. Okay, and or you can go with the phasor diagram. Go by the phasor diagram method also, it's quite easy. You've done all these things in vectors so many times that it should not be a problem. So you can see that this will be your net amplitude. Now you can use this, that this angle will be equal to this angle, and because this 60, this will be 30 each. Okay. And then drop a perpendicular from here. So you can see your A net will become twice of this part, this or this. Okay. So that is A cos 30. Like that. So that's the same. And this A is equal to 2 millimeters. So that's as simple as that. Okay. Now, so that's the first part done, the net amplitude. Now you can also see that what will happen is that your resultant wave equation, therefore, which you're getting by the superposition of these two, will become this thing. It will become 2 root 3 sine omega t minus kx plus pi by 12 हो जाएगा. Actually, that phase constant is not important over here, but this is the wave equation. So from this, you can also see that the net power will become this thing, 2 root 3 square into omega square P mu. Whereas P1 was equal to P2, this is basically half square root T mu omega square into net amplitude square, and this is T square. So this ratio is basically net amplitude is to this whole square. So it is basically 3:1. Very correct. So that's good. So that's the second part, the net power. And now you can also see that omega, which is equal to 2 pi f, is given to us us in the question as 200 pi radians per second. कौन सा 2 pi by 6 नहीं होगा बेटा. pi by 6 is, oh sorry, हाँ correct, it is pi by 6, my mistake, yes, it's 2 pi by 12, 1/12 of a full phase. This is pi by 6, this will be basically 30 degrees. Right. Yes, Ashwin, that's correct. Aditya. And so this is telling you the frequency of these waves is 100 hertz. This is telling you that the wavelength is 80 centimeters. You'll also know that the wave speed, which is square root t by mu, is also equal to f lambda. So it is 8,000 centimeters per second, or you can see it is 80 meters per second. So this is the propagation speed, this is the frequency, this is the wavelength. So these are the additional informations about the resultant wave. Very simple, nothing tricky about this. Formula based. In fact, ये वाला और भी ज़्यादा simple था because the individual amplitudes were also same. So when you are noting down, make sure you made this correction over here. I had written this pi by 12 by mistake earlier. This is pi by 6 and not pi by 12, as you pointed out. Okay, so we've covered all the 3 parts of the question. Now we come to the more typical type of question where there is more calculation we have to do. It's not so formula based. We have to do more like a understanding based or a derivation based kind of thing. So a situation which looks like more like a physical example, what is actually happening. So we have a very long string extending from x equal to 0 to x tending to infinity on this side. So we have a thin uniform thread kind of thing, which is under a tension of T equal to, let us say, the tension here is 250 newtons, and the linear mass density is 1 gram per centimeter. Now what is happening is I'm going to have a source S1 and another source S2 at some x equal to d, and then we'll talk about a general point P which is at x equal to x. Okay. So two simple harmonic oscillators S1 and S2 are attached at points x equal to 0 and x equal to d as shown. They individually create transverse waves of A1 equal to 1.2 millimeters and A2 equal to 1.6 millimeters respectively at identical frequencies of 100 hertz. So we have to write the equations of the individual waves created by them. Let's say y1 and y2 at a point P x equal to x, where x is greater than d. Okay. So do this and find the net amplitude due to their superposition. Okay. Assuming S1 and S2 oscillate in phase. Given case 1, this d is equal to 12.5 centimeters, and case 2, d is equal to 25 centimeters, and case 3, d is equal to 50 centimeters. So in each of these three cases, we have to calculate these two things. We have to write the equations y1 and y2 of the individual waves created, and from that we have to find out what will be the net amplitude due to their superposition. Okay. If they oscillate, the two sources are oscillating in phase. So in that case, what will be the net amplitude due to their superposition? Okay. So just start working on this question. So remember how we derived the equation of a sinusoidal traveling wave. In the first few lectures, in the second or third lecture, we would have derived that equation. That if a simple harmonic oscillator is tied to one end of the string and is oscillating according to the equation A sine omega t plus phi, then how that creates a wave that is traveling along the string with a sort of relationship, A sine omega t minus kx plus phi, that kind of thing. So do the derivation of that for each of the sources S1 and S2, and from that you will understand how to come to the interference point. That is, how to find the net amplitude at a point like this. Another hint to you over here, just make sure you understand this point. Listen carefully to what I'm saying. S1 and S2 दोनों source phase में है, but that doesn't mean that the wave that they are creating at the point, the individual waves y1 and y2 that they are creating at the point P, they are not going to be in phase. Can you tell me why? S1 and S2 are two oscillators that are oscillating in phase, but I'm saying that the waves that they create, y1 and y2 at the point P, such waves will not create disturbances which are in phase. Can you understand why? Now just imagine the physical situation. दोनों oscillators साथ में oscillate कर रहे हैं. That means they are going through the mean position simultaneously. They are reaching the extreme position simultaneously. But the disturbance that they are propagating through the point P, that's not in phase. Can you understand why? Because there's a delay from the source to a general point, and that delay depends on what? It depends on the distance. Now जो wave S1 से start हुआ है वो ज़्यादा distance travel कर रहा है, और जो wave S2 से start हुआ है, that is reaching faster at the point P, because it's traveling a lesser distance. So even though the sources are creating disturbances which are in phase, but those disturbances are not reaching in phase to a general point like P. They are reaching with some kind of time delay because they're traveling through different distances. So that is going to create phase difference, and that is why I've asked the net amplitude for different values of distance. In one case 12.5 centimeters, in another case 25 centimeters, like that. So that's why you have to understand that the sources are in phase, but the waves created by them will not be in phase because the sources are not located at the same point. So at a point like P, the wave coming from S1 is having a different phase compared to the wave coming from S2, because the wave coming from S1 is traveling a longer distance compared to the wave coming from S2. So even though the sources S1 and S2 are given to me in phase, but the waves created by them at a general point like P will not be in phase. Okay, so keep that in into account. Take that into account when you're writing the wave equations, and you'll understand how to get the phase difference. Yeah, so let's start with the first part, people. Hope you're writing the individual equation. So see, basically what is happening is, let's start with all the basic information. Frequency of both the sources is 100 hertz. Okay. And the propagation speed in the medium is T by mu, which you will write as 250 newtons divided by 1 into 10 raised power minus 1, because you will convert this to kg per meter. Okay, we've been through this before also. So just reminding you that when you convert gram per centimeter to kg per meter, you get a factor of 1 gram per centimeter becomes 10 raised power minus 3 upon 10 raised power minus 2 kg per meter. So it becomes like this. So the wave speed becomes 50 meters per second. Okay. So that also means that lambda, which is V by F, will become 50 divided by 100 in meters, or 50 centimeters. Okay, so lambda is 50 centimeters, frequency is 100 hertz. That's given to us. Okay. So from that, we can see that omega will be 200 pi radians per second, and k will be equal to pi by 25 radians per centimeter for both the waves, for both S1 and S2. So that's the most basic thing. Now it comes to writing the equations. So when it comes to writing the equations of the waves, now what is happening here is you talk about the individual waves. Okay. So suppose मेरे पास सिर्फ source S1 होता, what kind of wave equation it would create? Let's understand this. So suppose only at the origin I have the source S1, which is oscillating with an amplitude E1 equal to 1.2 millimeters, frequency equal to 100 hertz, and the string has the tension 250 newtons and the linear mass density 1 gram per centimeter. Okay. So suppose the equation of the SHM for source S1, which is an SHM, is E1 sine omega t. Because suppose I switched it on at this. Okay. This is the equation for this SHM. S1 is started at t equal to 0 from the mean position. So it's so that E sine omega t plus phi now. So उसमें phi को 0 लिया है. So now what kind of wave equation it would create? It would create a wave that is traveling like this, which at a general point like P at x equal to s, it would create a wave by 1, let's say. It would be E1 sine omega into t minus x by v, as omega, because this distance from here to here is x. So it's traveling a distance x. So that would create a delay time of how much? X by v. So the wave equation would become like this. Y1 would be E1 sine omega t minus kx. Where now we know all the terms. E1 is 1.2 millimeters. Omega is 200 pi radians per second, and k was pi by 25 radians per centimeter. All this information is known to us. Okay. So ये हो गया मेरा y1 का equation. From the fundamental derivational kind of method, or from the conceptual method of source S1 oscillating with angular frequency omega and amplitude A1 at this point. So at a distance from that source, distance x from the source, what is the wave equation is like this. Now similarly, you write an equation for y2. Okay. So similarly, you do this thing for, so do a similar analysis for the wave created by S2 as an isolated source, okay, as an individual isolated source. Then we will see the superposition, and the superposition thing will just come by formula. We don't have to do any derivation and all that. So hope it is clear up to date up to this point. A क्यू 4 पाई होगा k is ओमेगा बाई v ना, ऐसे भी लिख सकते हैं. और v कितना आया था अपने पास 50 meters per second. So it is 200 pi divided by 50 in radians per meter. So it's 200 pi divided by 50 in radians per meter. So that's the same thing as 100 pi by 25 radians per meter. So I've taken the unit but in per centimeter. So वो convert हो गया सर. और lambda से निकाला था. We just done this calculation above here. So again, you have to be very careful about the units. This calculation I did earlier. Now this will apply to both the waves because both the sources are having same frequency. And the waves are passing in the same string. So obviously B is the same. So given the frequency and given the tension and the linear mass density, all these three things given, we can now calculate omega's value and we can calculate K's value because we can calculate lambda from here. So this is the sequence of solving these things. So again, all those fundamentals become important. That frequency is the property of the source. Wave speed is the property of the medium. Tension or mu पे depend करता है. And therefore lambda is affected by both the frequency of the source and as well as the properties of the medium, T and mu. So the value is correct now, no? Pi by 25 radians per centimeter. In meters, वैसा हो जाएगा. It will become correct. 4 pi. You can also say that's the same. In SI unit, this would become 4 pi radians per meter. That's correct. What you're saying. In fact, you can just write it 4 pi radians per meter. No problem in that. Now, similarly, what will be the individual equation for the individual wave created by source S2? So, उसमें बस एक चीज आपको modify करना है. That is, the source S2 is not located at 0. It is located at D. Rest of the things are the same. P, mu, everything is the same. But the source S2 is located at the point x equal to D. So, when the wave reaches the point x equal to x, that wave has only traveled a distance of x minus d instead. It's not traveled a distance of x. So suppose the S2 source has an equation which is given by E2 sine omega t. Now why we are writing it like this? Because it is in phase with the source S1. So S1 को हमने sin omega t लिखा था, तो इसको भी हम sin omega t लिखेंगे. Suppose we assume that S1 was sin omega t plus pi by 2, then S2 also we should have written as sin omega t plus pi by 2. Now the important thing is that the two sources are in phase, okay, where specifically now we know that this amplitude is 1.6 millimeters, it's a different amplitude. However, the frequency is the same. So it is 200 pi radians per second. So now at the point P, what kind of disturbance will be? So this is the SHM equation. This is the SHM of the source S2. That is this equation. Now from this equation we have to convert it to a wave equation. So it creates a wave which has a general equation, let's say y2 at x as a function of time, that becomes e2 sine, but it's traveling how much distance now? It's traveling a distance of x minus d. But better we write it a bit more systematically. So it is omega into t minus x minus d by d, where of course omega by v becomes k, which is basically 2 pi by lambda, where that becomes again 4 pi if you are expressing in radians per meter, or pi by 25 if you are expressing in radians per centimeter. That's completely up to us how we want to express it. So wave equation y2 क्या हो गया है, थोड़ा सा और systematically अगर मैं लिखूं, it becomes a2 sin omega t minus k into x minus d, given like this. Or if I write it in a slightly more systematic manner, because d is a constant, the function is of x and t, the function is of x and t, so y2 at x as at a time t is becoming a2 sin omega t minus kx plus some phase difference delta phi compared to the first wave, and that phase difference is working out to be k into d. So as you can see, it depends on how far we place the two sources. So when this situation happens, this is called phase difference, which is happening by phase difference. As a result of what we call path difference. The two waves are traveling at different path lengths of d. सोर्स S1 से एक जनरल पॉइंट पे और सोर्स S2 से एक जनरल पॉइंट पे कितना पाथ डिफरेंस है, d का पाथ डिफरेंस है. So when you convert a path difference into a phase difference, okay, so basically the rule of thumb becomes like this, that path difference, we think of it like a term like delta x, because it's the difference in x. If that is d, then the phase difference, the corresponding phase difference it creates, delta phi, becomes 2 pi by lambda into delta x, or that is kd. So this is the relationship between a path difference of delta x and a phase difference it creates of delta phi. Path is converted into phase by multiplying by 2 pi by lambda. That's a simple kind of relationship that we should remember from this point of time. That whenever two waves are traveling a different path of delta x, then they have a phase difference as a result of that of 2 pi by lambda into delta x, or k into that. Okay. So now we have the individual wave equations. Okay. Now we'll work out each of this. Okay. Now you can see that for, and rest of the things are same, of course. Yeah. In this wave equation, your omega is 200 pi radians per second, and of course k we have written now. This is same. This is k. This is omega, and a2 is 1.6 millimeter. So we have got this term. We have got the term of phase difference in terms of the distance t, and we have got the individual wave equation. So our part 1 is done. Our part 1 of the question was like this. So I'm just concluding with the values. Okay. So individual wave equations created by source S1 and S2. So y1 will be equal to a1 sine omega t minus kx. y2 was sine omega t minus kx plus some phase difference, where now I have all these terms. E1 is equal to 1.2 millimeters, E2 is equal to 1.6 millimeters, delta phi is kt. Okay. Now we come to the individual parts, and of course omega was 200 pi and k was pi by 50 in radians per centimeter in CGS unit. Okay. So now from this we'll come to this each of the parts. So this is the first part's answer. Now case 1, our distance d was 12.5 centimeters. Case 2, 25 centimeters, and case 3 was 50 centimeters. So each of these cases we'll discuss about in detail. So now we have to apply this in the second part to each of these. Okay. So just go through this once and make sure you understand how we've written the equation of the wave 2, or the equation of the wave created by the source S2. Pi by 25. So नीचे I've written wrong here. Yeah, just make this correction before we continue, because we'll need these values. So let me take you through both the wave equations first. This is wave equation for S1, which we just saw earlier, just for your reference. Now similarly, your source S2 is not starting from the origin, it's starting a wave from this point. The wave which is starting like this, it's having an amplitude of this and a frequency of 100 hertz. So your SHM equation is this. This is your SHM equation. So that is why at a general point like P, where the wave is traveling through a distance x minus d, the wave equation is becoming like this. Or simplified further like this, or simplified even further like this. Okay, so understood now. Now you can just see in each of the, if the individual wave equations are like this. Now for each of these specific cases, you know there's a specific value of phase difference. So you will know what the resultant amplitude from the interference will result in. Okay, so let's go back and understand the second part of the question first, then we'll come back to this. Okay. So second part of the question में क्या करना था? First part we wanted to write the equation, so this part we are done with now. And the second part we want to find the net amplitude due to their superposition in each of these cases. We want to find the net amplitude in each of these cases. So this is that part. Okay. That we know the individual wave equations are this. Okay. Now we want to find the net amplitude for each of these, for each case separate. Okay. So you can see that relationship दोनों के बीच में क्या है, ये relation. So D का value substitute करो 12.5, you will get some phase difference. D का value substitute करो 25, you will get some phase difference like that. So all the data that you need for this part now is here. It's in this part. From here onwards, you can just use this information. Okay, so how much are the amplitudes you are getting? Just tell me. Case 1 में कितना आ रहा है? So in case 1, where you take D as, what was it, 12.5 centimeters, or that will become 0.125 meters. Your delta phi will come out to be pi by 2. Okay. And therefore your net amplitude should come out to be root of A1 square plus A2 square. So it should come out to be 2 millimeters. Because also our E1 was 1.2 millimeters and E2 was 1.6 millimeters. So this is what you should be getting for the first case. Okay. Similarly, for the second case, you will get destructive interference because D is just exactly half a wavelength. You can see. You can also see that here the important thing is lambda was 50 centimeters. So ये जो है ना, this is corresponding to lambda by 4. Okay. So that is why this thing you would see is corresponding to delta phi equal to 2 pi by 4 or pi by 2. Quarter of a wavelength, so quarter of a full phase. A full phase is what? 2 pi, so pi by 2. Similarly here, this one you can see is corresponding to lambda by 2. So my phase difference will become pi, so it will become destructive interference. Okay. So anyway, go by the formula based method also. Delta phi will come out to be pi. So your net amplitude should come out to be mod of A1 minus A2. So it should come out to be 0.4 millimeters. So this is the destructive interference case. So this is giving a practical situation of why it occurs like this. ऐसा क्यों होता है? We get destructive interference, we get constructive interference for different values of D. You can understand why that happens. Similarly, the third case you can see. In this case, D is a full wavelength. D is equal to lambda. So your phase difference delta phi will come out to be 2 pi when you calculate. So you will get your net amplitude as A1 plus A2 or 2.8 millimeters, which is your constructive interference. यहाँ पे your D, in this case, D is equal to lambda by 2. So that is why your phase difference is 2 pi by 2 or half a full phase. So there is always that relationship. Alright, so this completes the theory part and the examples I wanted to discuss today. So now next I would like to go back to the worksheets and the exercises, and if any doubts and things are pending, I'd like to complete that first before I move ahead. Okay. So from the first set of assignments I had sent, are there any doubts? Please send me if you do have. But I also want to explain something visually over here in this example, so I'll come back to that. So let's understand one thing. So you understood why in the second case there is destructive interference and in the third case there's constructive interference. But let's also understand a little bit more interestingly. If we take case 2, where your D was equal to 25 centimeters or lambda by 2, you can see that in this case, suppose my source S1, which is located at x equal to 0, that is creating a wave which is like this now. Suppose. That's creating a wave like this, which is y1 is equal to E1 sine omega t minus kx, where this is one full wavelength and this was equal to 50 centimeters. Calculation wise we will see, or that's the same as this, or that's the same as this. These are all one full wavelengths, crest to crest or trough to trough. Now here the individual wave by 2, how would that one have looked? Let's also understand that. तो अगर मैंने y2 वाला वेव इंडिविजुअली देखा होता because of the source S2, I would have seen that the source S2 is located somewhere here. S2 is located here at x equal to d, where d was 25 centimeters. And what kind of wave this source would have created? Let's understand that. So this particular thing would have created a wave it would have looked like this. Of larger amplitude. This kind. So if we superimpose these two, so now if we want to look at the net effect of the two together, that would look like this. Because the distance d is exactly equal to lambda by 2. So what is happening is, as a result of that, this is where S1 is located and it's creating a wave shape which is like this, let's say. Creating a wave shape like this, y1. Then the corresponding second source, S2, would have been over here. And that would have been creating a wave shape which is like this. You can see the crest and trough are overlapping everywhere. This is physically what would have been happening. So this wave would have been y2 equal to a2 sine omega t minus kx plus pi, or that is actually becoming minus a2 sine omega t minus kx. So you can see that यहाँ पे जहाँ इसका amplitude plus a2 है या displacement plus a2 है, this one is minus a1. यहाँ पे जहाँ इसका minus a2 है, this one is plus a1. So you can see that the net amplitude, so the resultant wave actually will be like this. These are y1 and y2. So the resultant displacement, which is coming from the superposition of these two, will be actually like this. It will be something where they are overlapping. It will be something like this. The larger amplitude A21 dominates everywhere. Okay. So this is my net y, which would have come out to be E net omega t minus kx plus pi आ जाता है यहाँ पे, where E net would come out to be mod of A1 minus A2. That in this case would become A2 minus A1, which is 0.4 millimeters. Okay. And your phasor diagram would have looked like this. Your E1 is 1.2 mm, but your E2 is at a phase difference of pi, and like this. It's at a phase difference of pi, but the amplitude is 1.6 mm. So your resultant amplitude is becoming this one, but it's an opposite phase with the first one. So that's why in the resultant wave equation you have this. That's all. Similarly, if you draw the case 3, now you will see that your source S2 is not here, it's here. So the crest and crest are overlapping and the trough and trough are overlapping. So So this is what we mean by saying that y1 and y2 are overlapping while they are exactly out of phase. Okay, so here what is happening? You can see from the diagram that the waves y1 and y2 are perfectly out of phase. They're perfectly out of phase or in opposite phase. So you can visually understand in this why that's happening. Similarly, if you do the analysis for case 3, you will understand that case 3 meant, I'm just quickly doing it in rough on this side. In case 3, something like this would happen. If your wave y1 is creating a pattern like this, the snapshot picture of y1 is like this, suppose. In the snapshot picture of y2, the source S2 would have been here. Okay, so y2 would have been like this. They're in phase. Right? So our net would become like this. The net having a much higher amplitude. That's how your case 3 would look like, where d is equal to lambda. So your phase difference is equal to 2 pi. Okay, so understand this diagram, or if you want to make a note of it. And now tell me anything in set 1 of the assignments, any questions you want to discuss in particular. I'll start with those then. Otherwise, there are a couple of questions that I want to discuss anyway. Okay, so if you finish writing this down, come to the assignment set 1, worksheet number 1, and let's start with question number 7. Okay, so come to assignment set 1, worksheet number 1, okay, and question number 7. So just go through that question, I'll explain it to you. So you have a string which consists of two symmetrical sections of length L by 2 and L by 2. So this length is L by 2, this length is L by 2. This has a linear mass density of mu naught by 2, and this has a linear mass density of 3 mu naught. And the common tension in the string, because the junction will have net force 0, so the tension is same on both sides. So this tension everywhere is equal to F naught. So if we create a small pulse at one end, we have to find the time taken. So if we create a pulse over here at t equal to 0, it starts traveling like this. We have to find the time at which the pulse will reach you. So it's very simple that the total time taken will be the distance traveled L by 2 with a speed v1 in this section, plus the distance traveled L by 2 in the heavier string with the speed of v2. So this total time will be L by 2 into 1 by v1, okay, which is 1 upon square root f naught by mu 1 plus 1 upon square root f naught by mu 2. Now just substitute over here. So T will become L by 2 square root of mu naught by f naught into this mu 1 at a factor of half and this mu 2 at a factor of so this will come in the denominator and this one will come in the numerator. It should be 1 by root 2 plus root 3. So this should become your answer. This should be the time taken. So many different ways of expressing it. The way they have expressed it in the answer is taken 1 by 2 common from this also. So L by 4 square root mu naught by f naught, because you've taken 1 by 2 common outside. So 1 by root 2 into 2 becomes root 2 and root 3 into root 2 becomes root 6. No, something wrong. That is not correct. No, that's not correct. So that's not the correct answer. The correct answer will be this one. It should be the correct answer. Anyhow, that's just algebra at the end. The concept is this part. Don't think you should have any difficulty in any of the other questions in this sheet. Now let's come to question 2 and question 3 of the next sheet. Next, let's come to sheet number 2. Let's start with question 2. We will also discuss question 3. Right, so have you gone through question number 2? So you have a traveling pulse like this in this question. Which is in the form of a asymmetrical kind of triangular shape. So that triangle is something like this, suppose. This is the triangular shape. And there is a rigid boundary present over here. At the given instant t equal to 0, this is the situation. This is traveling at a speed of 2 centimeters per second. And this distance here, and also this height, all these are given to us. Okay, Aditya, I've got your messages. I will come to those questions. Okay. So in this diagram, this is 1 centimeter. This is also 1 centimeter. This height is also 1 centimeter. But this is 2 centimeter. Now we've been asked to find the shape of the pulse at t equal to 2 seconds. And the particle speed on the leading edge at that instant is depicted as how much? So we have to find, so you have to draw the shape at t equal to 2 seconds, and you have to find the particle speed at the leading edge. Let's understand what that also means. So at t equal to 2 seconds, if you go with that method we had discussed of superposition, this is where the so-called boundary is. Then understanding it as a superposition of the forward pulse and an imaginary reflected pulse, the forward pulse should be here. Its peak should be over here at the boundary. This is where the forward pulse should be at this instant of time. Likewise, the imaginary reflected pulse would be at a position like this. Should be now see why exactly it should be like this, because when they overlap fully, they should completely cancel each other. That is the whole point of this. You understand? At an instant when they overlap, they should fully cancel each other. That is the whole point. Is that correct? No. What should happen is at this point where the boundary is located, they should always be cancelling each other. So the reflected one should not be like this. It should be symmetrical in such a way that at the boundary they are always symmetrical. So that at the boundary the resultant is always zero. That's what. So the reflected one has to be like this. I mean the imaginary inverted one has to be like this. It's only in this kind of situation where they will always cancel each other. At this boundary position, or at this symmetry position, if you take this one traveling like this, and this one traveling in the opposite direction, they will always superimpose such that they will cancel each other at x equal to 0. The net displacement at x equal to 0 will always be 0 because it's a rigid boundary point. Okay. So now if you understand how the superposition will look like, you realize that the resultant of these two here will look something like this. Then up to this point, there's no effect of the red line because the red line is 0. But then it becomes like this. This is the resultant. So that is why the actual thing will look like half of this. So this is at t equal to 2 seconds. So the actual thing will just look like this. its height will become 0.5 centimeters. Sorry, it was 2 centimeters per second. My mistake. It was 2 centimeters per second. This will be the picture which I have shown you when the peak is over here. So it's traveled 2 centimeters. So it won't be at 2 seconds. This will be at 1 second. This will be at t equal to 1 second. My mistake. Because the peak has traveled 2 centimeters. So this will be 1 second. So I'll show it to you how you will get at t equal to 2 seconds. At t equal to 2 seconds, the blue one's peak has actually traveled 4 centimeters from here. So when it travels 4 centimeters from here at 2 seconds, this point has gone here. So it's like it's gone 2 plus 2, so that will look like this. Similarly, the actual question is at t equal to 2 seconds, not 1 second. So at that instant, the forward pulse would actually look like this. It has gone beyond by 2 centimeters. So it has gone like this. So it's gone 2 centimeters further. So the imaginary inverted pulse, where would that one be? That one would be, this is another 2 centimeters from here. So this peak has gone from here to this point. So they've actually just crossed each other at this instant. Like this. So the superposition will actually result in, you're just left with the red one. It's like this. So this is how this superposition picture is looking at t equal to 2 seconds. So the actual picture at t equal to 2 seconds of only the reflecting pulse will look like only the left half of this. It will look like this one. The inversion process has actually got complete. That's how. This. And this is traveling with the speed v. That is 2 centimeter per second. Now the leading edge से क्या मतलब है? This edge. So you have to find the velocity of this edge at that instant. So let's say this leading edge point is P. We have to find the particle velocity at that point P. Okay, hope this is clear. Now we have to find the particle velocity at that point. So particle velocity कैसे निकालेंगे? For that we need del y by del t at that point. So how do we find out del y by del t? So you can see in any wave equation, this is an important thing. Any traveling pulse or wave, the equation is of the type f of kx plus minus omega t, like this. So for the above pulse that we have shown, like this one, this is the shape of the pulse. It's 2 by 1 by 1. It's traveling along the negative x direction. So you can see that this will be of the type some function into kx plus omega t, because it's traveling with a velocity of omega by k along negative x axis, like this. Okay. So for this, the particle velocity at any point is basically what? It's del y by del t. So differentiate this partially with respect to time. You will get omega into derivative of this function into kx plus omega t. This is the particle velocity at any x at any time t. Now also you'll see that the slope of the y versus x graph, which is basically the snapshot picture, which is this only. This is a snapshot picture at that instant. This is the snapshot at t equal to 2 seconds. So that snapshot picture slope at any point will be what? Del y by del x, because time is constant. So you are differentiating y with respect to x, keeping time constant. So differentiate this partially with respect to x. So it is k into f prime, kx plus omega. Okay. So now we are looking at this particular point, which is point P. So whatever the x coordinate of that point is, it's fine. ये वाला point P है, ठीक है? So as the wave is progressing like this, you can see that this point will have a downward particle velocity like this. But how do we calculate that downward particle velocity? We can calculate it from the slope, because you can see the graph. The graph is very simple. The slope at that point is what? It's -1. No? We have drawn the detailed graph. So if you see at this point, at the point P, which is the leading edge, the slope of the graph, that is del y by del x, is equal to how much? -1, because this is a straight line of 1 by 1. It's this thing slope. So this angle is 45 degrees at that point. So you can see the slope is -1. So therefore, the particle velocity now you can see that the relationship between particle velocity, which is del y by del x, del y by del t, my mistake. Okay. At the point x equal to whatever the x coordinate of that point p is, at the time 2 seconds will be, from this equation you can see this is omega f prime and this is k f prime. So it is nothing but omega by k times del y by del x at x equal to xp at t equal to 2 seconds. And this whole term is nothing but the slope of y versus x snapshot at the point p at the time t equal to 2 seconds. So the snapshot that we've seen above at the time 2 seconds, at that leading edge wala point, what is the slope? It was in fact equal to -1. So the particle velocity should also become like this. So the particle velocity should become omega by k times the slope. And that slope over there at that time was -1. So the particle velocity should be negative in direction and omega by k in magnitude. Now also, omega by k is nothing but the propagation speed, which was 2 centimeters per second. So this was 2 centimeters per second. So with the proper algebraic sign, the particle velocity at that point should be minus of 2 centimeters per second. Or you can see that the particle velocity will be 2 centimeters per second, but going downwards. Whereas, if I'd asked you for some other point, the particle velocity would have been different. Okay, I'm just showing you as another example. Suppose I asked you, instead of that leading edge point, I asked you a point which was somewhere in between the peak point and where the boundary wall is. We can see this V with proper algebraic sign is minus 2 centimeters per second. Now also we saw that this is the snapshot picture at the moment t equal to 2 seconds. At the moment t equal to 2 seconds, this is the snapshot picture, which is traveling like this. So this point we saw had a particle velocity in the downward direction, which was that much, which we calculated. Okay. But suppose I ask you some other arbitrary point, like I ask you this point here, what is the particle velocity here? What is del y by del t at the point x equal to xa, whatever that is, at the time t equal to 2 seconds. So abhi kya karna padta, we'd have to calculate like this. This would be again omega by k times the slope at the point E at the time 2 seconds. So what is this slope now? This slope would be a positive quantity. This is 1 centimeter, this is 2 centimeter. So this slope would be plus half. This is 1 centimeter, this is 2 centimeters. You can see as this wave is propagating like this, the point A would tend to go up, as you can see. This pulse would change shape like this. So the point A would be tending to go up, and it would have a velocity in the upward direction, which would be this quantity, omega by k into that slope. Okay. So omega by k into that slope would have been positive of 1 by 2. So it would have been positive half of omega by k, and omega by k was 2 centimeters per second, which was the wave speed. So it would have been plus 1 centimeters per second upwards. That would be the particle velocity at the point E. Whereas at the leading edge, the particle velocity with proper sign is in fact minus 2 centimeters per second, or we can say it is 2 centimeters per second downwards. Okay. So this is another additional, slightly tricky thing that you should know as a method of calculating particle velocity. For any given equation, any given y equal to f of kx plus or minus omega t, you can see that the particle velocity is del y by del t. So that is plus or minus omega f prime kx plus minus omega t. Whereas the slope at any point, that is del y by del x, is k times f prime kx plus or minus omega. Okay. So the relationship between these two differentiated partially and all that, we don't have the necessity to do all these steps because we can directly see from the graph what the slope is. So we can relate the particle velocity with the slope at a point. So particle velocity at a point, which is del y by del t, becomes, depending on whether the sign is plus or minus omega by k times del y by del x, which is nothing but the slope. Okay. So the particle velocity and the slope of the instantaneous snapshot have this relationship. So particle velocity at x equal to x, t equal to t is equal to omega by k with a sign depending on the sign of the terms in between. That many times the slope of y versus x snapshot picture at the instant t. Okay. Slope at that point x, where we are calculating the particle velocity. So this becomes another additional little concept you should know. That was the point of discussing this question. Okay. Aditya, I have received your doubts for the second set, but I will be coming to that set at a later time. But okay, today there are few questions that I wanted to discuss apart from your own doubts of the first set. Okay. So let me complete the discussion about these, then I will come back to that. Okay. But you don't have any doubts pending in worksheet 1, I mean the set 1, is it? Okay, Aditya, you cleared that in last class. It's fine now. So instead of question 3, let me come to question 4. Both are of the same concept, but question 4 is slightly more like a numerical problem. So let's do that. So same thing, sheet number 2 of set 1. Yes, question number 4. So wave travels on a light string. The equation of the wave is given by this. It is reflected from a heavy string tied to one end at x equal to 0. So you are given one equation like this: y equal to e sine kx minus omega t plus 30 degrees. Okay. This is reflected from the junction with the heavier string, and that junction is at x equal to 0. That junction is at x equal to 0. Now notice that this is a wave that is traveling along the positive x direction and is getting reflected from the origin. That means this must be traveling in the negative side. Okay, so that means the lighter string must be present on the negative side of your origin, and your heavier string is present on the positive side, on the right side of the origin. So the junction point can be denoted by x equal to 0, and a wave traveling along the positive x direction, okay, on the lighter string is getting reflected. So this is your incident wave, which is denoted by y over here. This is the incident one, whose equation is written above. Now, additionally, what information is given to us in question 4, that 64% of the incident energy is reflected. Okay. Then the equation of the reflected wave is how much? Okay. So 64% of the incident energy is reflected. Okay. Then equation of reflected wave we have to find. We have to find the equation of the reflected wave. Okay. So let us say that the reflected wave coming back in the same string from the boundary, the reflected wave is having some equation yr, let's say, okay, and the transmitted one is having some yt. Okay. And let us also understand. So the incident one had the equation which was already given to us. It was E sine kx minus omega t plus 30 degrees. So the reflected one will be y reflected equal to some reflected amplitude into sine same k and same omega. Now understand why it's the case, but some phase difference, let's say delta phi. So why they should have the same k? Because obviously omega of incident will be same as omega of reflected and omega of transmitted, because that is just the frequency of the incident wave. Omega will be the same as the omega of the reflected wave, same as the omega of the transmitted wave, because all three have common frequency. All the oscillations are happening at common frequency f. Okay. But what will happen is that the incident and reflected waves have the same value of wave speed, because they are operating in the same string. Okay, so if this string had linear mass density mu1 and this string had linear mass density mu2, and obviously you can see mu2 is greater than mu1. Okay, So all this being assumed over here. So because these two, the incident and reflected, are operating in the same medium, they have the same wave speed. So if they have the same wave speed and they already have the same frequency, they must have the same k also. So they have same wave speed, no, not same wave direction, because one is positive and one is negative, but magnitude of the wave velocity, that's the wave speed, square root t by mu 1. So that means they have also the same k. They will have the same lambda and the same t. Whereas the transmitted one will have a different value of v. Okay. But the transmitted wave that has a v prime, let's say, of square root t by mu 2. Okay. So that is square root of mu 1 by mu 2 times. I mean, all this is not required here because we have to answer only about the reflected wave. But in case you were asked about the transmitted wave, you have to understand this. This is this. Okay. So it has a different wave speed. It has a different speed given by this, and therefore it has a different k or a different lambda. K, which is, let's say, k prime, which will become omega by v prime. So that will become, now v prime was this now, so this will become square root of mu 2 by mu 1. This will become square root of mu 2 by mu 1 times k. It will be a different k. So this one's angular wave number k prime will be this, or it will be this in terms of the other two k. Okay. So anyway, that's not going to be a concern for us here because in this particular question we've only been asked about the reflected wave. Okay. Now for the reflected wave we have to calculate two things. One is the amplitude and the other is the phase constant delta phi. Now reflection यहाँ पे कैसे हो रहा है? It's happening from a rigid boundary. So that means there should be phase inversion. So ये factor कितना होना चाहिए? It should be, sorry, this is plus now. Plus. So this is in the opposite direction. So what should happen? The incident wave and the reflected wave should have opposite phase at the boundary. Because it's a rigid boundary. And the boundary is which point? X equal to 0. So you can see that y at x equal to 0 is a sine 30 degrees minus omega t, and y reflected at the boundary point is how much? It is some reflected amplitude into sine 30 degrees plus omega t. Now this phase should be an inversion of this phase. Understanding? So 30 plus omega t should be equal to, oh sorry, there's a phi also, my mistake. You have to take that phase constant into account. Okay, just give me a second. I'll have to reshare the screen because it's getting stuck. Just give me a couple of minutes. Restart that program and share it again. Okay. So coming back to this, these two equations should be of opposite phase. So opposite phase means ये जो भी वैल्यू दे रहा है ये उसका ऑपोजिट देना चाहिए. So that means sine of 30 degrees minus omega t plus delta phi should be minus of sine 30 minus plus should be minus of sine 30 minus omega t. Okay. So basically what I'm saying here is that sine of omega t plus 30 degrees plus delta phi, whatever this delta phi is, should be, now take the minus sign inside, so this becomes sine omega t minus 30 degrees, like this. Okay. So sine omega t plus something is equal to sine omega t minus 30. So that means this delta phi should be how much? This phase difference delta phi should become how much? It should be minus 60 degrees, or it should be minus pi by 6. Okay, so that's one thing. And the second thing is that it is also given to us that the power of the reflected wave is 64% of the power of the incident wave. The power of the reflected wave will become half square root p mu1 omega square into e reflected square. That should be 0.64 times. Same thing, half square root p mu. Only difference is amplitude is t. So you get the simple relation that this amplitude square should be 0.64 times this amplitude square. So amplitude being a quantity which only has modulus, no sign, so this should be 0.8. So now you got this and you got this phase constant. So you will understand the equation of the reflected wave. The reflected wave will have an equation of 0.8 e sine kx plus omega t plus 30 plus 60. So ये plus 90 हो जाएगा. Just hang on a second. Let me check this. Oh sorry, it should be minus 30, not 90. This should become minus. This should be the reflected wave because the incident wave was this. this was the incident. So you can see that from this, if you compare the two, you can see that the power of the reflected wave will be 0.8 square times the power of the incident wave. This one was the incident. This is the reflected one. And you'll also see that the reflected wave at x equal to 0 is 0.8 e sine omega t minus 30 degrees. And the incident wave at x equal to 0 is e sine 30 minus omega. So they have a phase inversion. So there is phase inversion between. Okay, so this is like a slightly more typical type of question. Okay. We had taken a simpler version of this when we understood the derivation of reflection / transmission at a junction point like that last time. But this is a slightly more complicated version. Okay. So just keep note of this and go through these questions once. And next time we will start with the discussion of the set 2 of your assignments. Okay, the worksheet set 2 of your assignments and anything pending in HC Verma, and then we will move on to standing waves, which is the last part of transverse waves syllabus. All right. So next lecture also, most of the lecture will probably go in completing the doubts and doing some discussion of some additional questions from both the set 2 of your assignments as well as your HC Verma, and also some questions from the module we can pick up. And after that, it will take a lecture or two to complete the standing waves portion, which is the last part of transverse waves. So that will complete the first chapter of wave mechanics, and then we'll move on to sound after that. Okay. That's it for today. Thanks, people.